Hello everyone. Our project is on breast cancer image classification. Our team members are Chaitanya Vardhan Kandula, Rishi Chaudhary, Saranya Selvaraj. This project is aimed at classifying a CT scan image of breast skin tissue and predict if that image belongs to malignant class or benign class. The dataset is obtained from Kaggle. We have applied all the techniques we have learned in class to build and improve the prediction process. The original dataset is obtained from Kaggle, which had over 200k images. Considering the file transfer speed, we had reduced our training dataset to around 40k images. Even though majority of the images has dimensions of 50 into 50, a handful number of images have a different size. We have excluded such images from our analysis. The class an image belongs to were embedded in the file name. We extracted the image class from the name using the code snippet mentioned below. Here is the snippet of the dataset directory. The dataset has 279 folders and each folder represents the CT scan of tissues for each patient. Each patient directory has two folders 0 and 1, which is 0 for benign and 1 for malignant. Next slide, please. The data obtained has imbalance of 4:1 between benign and malignant classes. Usually in medical industry, for disease prediction, we have to do number of trials for a specific test. So it is natural to have less success rate. Since ours is also a disease prediction dataset, we faced similar class imbalance issue. We had occurrence of 0, which is benign, which is more than malignant. To overcome this issue, initially we tried random undersampling. With random undersampling, we leave the minority class as such and reduce the majority class samples. But this resulted in underfitting issue, and also we couldn't learn all the features though we had many. Then we did random oversampling, where we sampled the minority class over and over again. Even though this caused overfitting, considering the benefits, we have used random oversampling for our model. So this plot explains the size of the training data before random oversampling and after random oversampling. In the first plot, we could see that for class 0, which is benign, there are 30,000 samples. But for malignant, which is 1, which has around 10,000 samples. The second plot shows the size after random oversampling, so which is almost equal, which is 30,000 samples for both category.
We also faced dimensionality issue. We had a large data set and around 1% of image had a different size than 50 by 50. We tried various ways like resizing all the image using ski image library, tried scaling and other techniques to normalize the image dimensions. With all those techniques implemented, the accuracy never went above 67%. As a mitigation technique, we have removed these images from our analysis. For hyperparameter optimization, we use probabilistic reduction. We begin our analysis with this reduction technology using talos. The below parameters were used during the analysis. This analysis took 2 hours to run and produce a model with 51% accuracy. After hyperparameter optimization, we selected a model with CNN layer 2, blue normal kernel initializer, where we got value accuracy of this model around 51% and value loss accuracy around 69%. We also used a brute force method. Since we had a big data set and brute force method could potentially take days to run, we made a strategy to split and run multiple small models. We will explain few models in this slide and we will provide a link to the cluster where all other models details are available. We ran analysis with CNN layer 2, 3, and 4, Adam optimizer with number of kernels 16, and other parameters as explained below. We selected a model with CNN layer 2. We got here testing accuracy around 85%. We also uh, did few more optimization in model 2 as a model 2, and with the kernel 16, 32, 48, 64, 88, and 100. But we got best accuracy with kernel 48. The accuracy improved than the first model, and we increased 85 to 86%.
So we further optimized the model. We have tried to optimize the optimizer, uh, which we gave the range values of Adam, STD, and RMS prop. So what we found out was with the optimizer, there is no further improvement, but then the best model selected had Adam selected as the best optimizer. So we also, these are just three models out of a total of 13 to 14 Talos hyperparameter optimizations that we are running in the cluster, and we ran in the cluster. The rest of the optimizations are available as a link in the document provided. But the other model, the one model that has been running for more than uh, 9 days, is this model N, where we have 1296 iterations that the model is currently going through, and it is close to 75% complete. And we are hopeful that in next couple of days it's going to be 100% complete. So these are the various parameters that we have given, starting from learning rate, number of kernels, batch size, dropout, and kernel initializers. So we're hopeful that this is going to improve our model performance significantly. So, but the initial set of iterations that we have gone through, we chose a best model that has two CNN layers, Adam optimizer, 48 number of kernels, and then a batch size of 50. And please note that we are not using any dropouts here. We found out in our analysis that not having a dropout layer has improved our performance significantly, even though it comes at a cost of slow model training. So we chose a model with no dropout. Even though it has dropout, we have commented in the code that we don't have, such that we don't have any dropout. So that was our model. So this model gave us an overall training accuracy of 87%, with a testing accuracy of 80.42%. The testing was done on 10,000 images, and the training was done on 40,000 images. So we were curious, as we used random oversampling. We were just curious if this is biased towards any of the model. So we went ahead and we predicted how the model is performing for class benign, which is class 0, and class malignant, which is class 1. What we got, the results are, I mean, the benign class accuracy is 100%, whereas the malignant class accuracy is 82%, which means random sampling, even though uh, telling us that it has less accuracy with malignant class, but 82% is considered to be a moderately good accuracy, considering that we have only tested for under 10,000 objects of images of malignant class. So considering this, and we still have to, we're still waiting for the model ends performance, model ends output. So once we get that, I mean, there are a couple of areas where we thought that we could really improve. One of such areas is the imbalance. So in order to overcome, we used a random oversampling technique, and we thought that the best way to overcome this would have been to instead of oversampling, we could have rotated the image, and then considered it as a new sample, so that we could have gotten more and more number of positive images of malignant from the existing data set. And the second element that we thought where we can improve is, instead of using ReLU alone, we could have included TANH also in the activation layer, and see how the performance is varying. So that was one hyperparameter technique we should have, or we could have implemented. That's where we from here wanted to improve this model on. And the third mitigation technique, the third area where we thought of improvement is removing, instead of removing the images which showed variation in dimensions, we could have tried scaling them and fit them into 50 by 50. That is one. Or we could have tried a different algorithm like OpenCV or some other elements. Even though the number of objects that we have excluded from the training data set are very minimal, like around 300, but 300 out of 9,000 images are considered to be a moderately good number. So with this, we'd like to thank Professor Dr. Shoibam, who gave us a chance to work on a project like this. And we are also glad that for the great learning experience that we have got from this class. Thanks a lot.
Thank you.